yet still more to come. We will have a detailed presentation, then we will transition to the question and answer portion. We have a lot to cover, so let me introduce you to today's participants. Giving today's Mars presentation is Rich Zurich, the MRO project scientist at the Jet Propulsion Laboratory in Pasadena, California. After his presentation, he will be joined during the Q&A session with Michael Meyer, Chief Scientist for the Mars Exploration Program here at NASA headquarters in Washington, and Scott Murchie, the MRO Principal Investigator for the Mineral Mapping Instrument, Johns Hopkins University Applied Physics Laboratory in Lowell, Maryland. So with that, I'll now like to turn the podium over to Rich for the presentation. Rich?
Thank you, Dwayne. Well, today I want to tell you about the recent observations by the Mars Reconnaissance Orbiter, which I'll refer to through the rest of the talk as MRO. And that mission, that spacecraft, was launched in August of 2005, and in March of 2006 entered a highly elliptical orbit around the planet Mars. After about 450 orbits using a technique we call aerobraking, we got into a nice circular orbit around the planet where we're flying on average about 180 miles above the surface of the planet. And from that position around Mars, we've been able to look at Mars with a spectral and spatial resolution that we've not been able to use over vast areas of the planet before. To do that, our spacecraft had to do a number of things. And in the first slide, you'll see the configuration of the spacecraft. And that big antenna on the top is 10 feet across to give you a scale here of how big the spacecraft is. And the reason for that is when you go to high spatial resolution, you want to return a lot of data. And this spacecraft has done that, setting new records for the return of data from deep space. The volume of data returned on the order of 80 terabits is comparable to many of the Earth data sets that we take routinely today. But given that it's coming back over hundreds of millions of miles in some cases, that's the achievement of this particular spacecraft. Now, to get to the science of this, first let me give you a little bit of view of what the science is about. MRO is a follow-the-water kind of mission. Sometimes that's interpreted to be find the water, and we've already done that, right? We know it's in the atmosphere. We know it's on the surface of the planet as ice. We now know that it's also in the subsurface of the planet, at least in the uppermost part. Whether that extends down deeper is one of the questions that we have and wanted to explore. So MRO is looking both at the atmosphere, at the surface, and probing the subsurface with a radar provided by the Italian Space Agency. In doing that, what we're trying to understand when we say follow the water is when was water on the surface of the planet? What did it do? How did it alter the planet when it was there? And how long was that period? From our past spacecraft, we see that there's evidence that Mars once had a wetter early climate. We don't know if that was a warmer and wetter climate. There is evidence that you'll see here from MRO and from other spacecraft that suggests that ice, the transition and movement of water as vapor from place to place on the planet and storage as ice on the surface, is a major player, at least in today's drier climate. When that transition occurred is one of the questions that we have to ask. And how rapidly or how abrupt was that change? And did it occur in just local areas, or did it occur regionally and globally? That's one of the questions that we'll focus on here in today's talk. I can't tell you about all of the things that MRO has been able to do in the 1 hour that I have. So we're going to emphasize this part of it, in particular, that ancient period of Mars history, some billions of years ago, starting from about 4 billion years ago, and a transition that seems to have occurred over the next few 100 million years, and how the record of that change has been preserved in the surface. And we find it by looking at both the shape, that is, the stratigraphy and structure of the surface, but also its chemical composition. So let's get started, and we'll go here to the next slide. Here you see that the Mars Reconnaissance Orbiter is the latest in a series of orbiters that have been monitoring Mars for over the last decade now. And in fact, we're following up on the discoveries that those made by taking instruments that can look at things in that higher spatial resolution that I told you about. In the meantime, you see that we've also landed craft on the surface, and one of the responsibilities of the orbiter, besides doing its science, is to find the best places for future missions to go, and that included, at the time that MRO arrived, the Phoenix lander, which landed on Mars just over a year ago and conducted its mission in the high latitudes close to the North Polar areas and such. And we'll talk a little bit more about how MRO did that as well. So let me show you a video here of the spacecraft as an artist concept of what it looks like in orbit around Mars. So if we'll go to that video, please. And here you see the spacecraft, solar panels out. That's required to power the payload so that we can run all of our instruments at the same time, look at the same place with the instruments at the same time, so that we can combine different kinds of data sets to understand what we're looking at down on the surface of the planet. As you're seeing here, we're coming up to looking at the payload deck of the spacecraft. This is the part that typically points to Mars. But this spacecraft does something more. It can roll left or right and therefore target different areas down on the planet. Some of the things that we see when we do that are our past friends, our past spacecraft that we've sent from the Earth to Mars. This has both a sentimental value, of course, but it also has the very specific value of trying to compare what we see once we're on the surface with what we can see from orbit. And when we go to look at future landing sites, for instance, we are trying to certify the safety of those sites and whether or not, for instance, they have large rocks that might obstruct the landing of those future vehicles. Now, in the next video segment, we'll show you a little bit more of the instruments that are on there. There are 8 scientific investigations that were selected for MRO, 6 instruments, one of those, as I said, provided by the Italian Space Agency, others from universities and NASA centers here in the United States. So what we'll take a look at is the instrument deck here, and we'll highlight on this video places where you'll see some of the instruments. The white box is the imaging spectrometer that looks at composition. The flashing yellow here is the context camera, which would be high resolution on a previous mission, but here is providing literally the context for which we can identify interesting places and then zoom in on them with even higher resolution. Over there on the left, in the pink, is our weather camera, which is looking horizon to horizon across, so that as the spacecraft flies along, you get 12 strips a day, one on each orbit. You put those together and you have a daily global weather map. Blue is the high-resolution camera that we have. You take one, if it's 20,000 pixels, projected down onto the surface from 180 kilometers up, and what you have is a spot that is about a foot across. That means you can start to resolve things that are the size of that table, including rocks that might be dangerous to future missions, but also exploring the details of this surface so that we can interpret what you see and test our hypotheses about how those surfaces formed. All right, let's go to the next video. There are a couple of instruments we won't have much time to talk about today. One of those is our climate sounder, which is profiling the atmosphere, taking its temperature and such. We actually used it when we first got into orbit to take a picture of our spacecraft. So this is it, scanning across. This is a thermal infrared image that is built up, and this is what that image looks like, and this is what your eye would see if you were able to look on the deck. So that was from Mars orbit, well above the surface of the planet. All right. So next, we're going to talk about some of the work that we did supporting the mission that landed just over a year ago, the Phoenix mission. In the next slide, we'll show you a set. These were the spacecraft that we looked at before, and these were the earlier ones, including the early Vikings back in the 70s, and more recently, of course, the 2 rovers that are still operating down on the surface. The next slide will show you the view that we caught of the Phoenix spacecraft while it was on its way to the surface of the planet. Now, this was a great shot. In fact, I think it's one of the great shots from the space program, and being able to capture that spacecraft in that moment as it flew to the surface. It had a very serious purpose that if something had gone wrong, we would at least be able to say, did the chute deploy properly? Was it fully deployed? That was part of our being